Hello there. My name is Al, and this may or may not be the third entry in a tutorial series entitled Topics in Linear Algebra. And what you're looking at right now is a colorful image of a beautiful woman, which is not the same as a beautiful image of a colored woman, although I do have that as well. The last two videos, assuming this is number 3, the topic of the last two videos was a little bit dry, simply just running over some definitions, and now this time we're going to start in with the concepts and the ideas of Euclid, the Euclidean system of geometry, which begins with postulates and axioms. I have it ready here. Okay, these are the definitions, and here now the postulates. These postulates are designed, according to this same book, to limit what we can do to essentially be the same things that one would be able to do with an unmarked straight edge ruler and a unmarked compass and colored pencils. So, towards that end, the first postulate, the first thing being deposited into the universe, is the following ability. Let it be granted that a straight line may be drawn from any one point to any other point. Okay? Now that is something that can be done with a straight edge ruler, unmarked, because we have the points. Let it be granted that a finite straight line may be produced, that means extended, to any length in a straight line. So that is, we may extend a given straight line indefinitely in any direction. Again, all that is required for that is a straight edge ruler. Let it be granted that a circle may be described with any center at any distance from that center, and that would be the ability granted to one by having a compass. There are two more postulates that didn't, I don't think, appear in the first book. It must have been later discovered that these two other abilities or items were being assumed, unknowingly assumed, that is, and so they were put in so as to make the system explicit. Now the axioms. In the modern form, Euclid's axioms contain only five. There are only 5 axioms. In this original version, there are 12. And I think I can tell you which ones are not in the of these are not in the current version. First axiom: magnitudes which are equal to the same are equal to each other. So that's the transitive property of equality. If A equals B and C equals B, then A equals C. If equals be added to equals, the sums shall be equal, will be equal. Okay, so equals like a plus, sorry, equals added to equals. If a equals c, then a plus b equals a plus c plus b. You know, if you can do that in your head, then you know what I'm talking about. If equals be taken away from equals, the remainders will be equal. So far, all of these are in the current version, I guess, of Euclid, of this book. This next one is not included currently, and so I assume that this one is unnecessary. It does not need to be stated as an axiom. It can be proven from the others. But I'll state it. If equals be added to unequals, the sums will be unequal. Okay, so if C not equal to D, then A plus C is not equal to A plus D. Similarly, for the taking away of unequals, these two as well are not in the current version. The doubles of the doubles of the same or equal magnitudes are equal. So 2 times a thing which is equal to, well, I can write it down. Yeah, program's not right. That just says so we start with A equals B. And the thing says the doubles of the same or equal magnitudes of the same or equal magnitudes, same or equal, are equal. So that means 2 times. I'm going to use the modern way of writing times. So that implies that we can double both sides and the equality weights the same. The halves, so we can also have halves, so we can go the other direction. So in fact, one way of writing this don't tell me I didn't. I can't believe I did that to myself. Which one is it? 25, 23. Oops. Here it is. And that's supposed to represent if and only if. But I made a mistake. I keep doing it to myself. Alright, I can fix that. I have a thing that I can type in and this would come out. And it used to work. Then I made one of my standard errors. The whole is greater than the part, than its part. Sorry. Now this bit is something which tells you something about the mentality and of the time and the system, and that is that this system admits no negative quantities. There are no negative quantities, only positive quantities, and so a whole, if it is made up of parts, it would be greater than its parts. So all that's saying is that if A equals, say, B plus C, those are the parts, then B is less than A and C less than A. Right? Same idea. No negatives, that's all that really says. Now this one I don't really understand. This two straight lines cannot include a space. Two straight lines. Oh, I know. Right. I figured it out. I thought I could. I thought I didn't understand it, and then it came to me. What it means essentially is, if I have two straight lines. Here's one. Okay. And here might be another one. We can't. This space is. I was thinking of space as an emptiness, but really, I think what it means is this here is an enclosed space, and two straight lines cannot enclose a space. There's no possibility of that. Go away. With two lines, no matter how you try to lay them out, you cannot enclose a space. Fair enough? So that's another axiom. And, well now, is that in the, I don't think that, there are only 5 in the current. And so far, this one I know is these two, and this one, that's 5. There must be more than 5. 2, 3, 4. Okay, but then this is not. None. These are not in the current version. No, right angles are equal, isn't it? This. Oh wait, now this might be this might have become a postulate, possibly, because I remember this is in there. I'm pretty sure. If only there was some way to look at your browser cache. If two straight lines meet a third line, okay, now this is the famous parallel postulate, or parallel axiom, which says something that any school child would immediately agree with. And any adult would as well. If two straight lines meet a third line, so as to make the two interior angles, these two, on the same side, less than 2 right angles, these two straight lines will meet if they be produced on that side on which the angles are less than 2 right angles. Got it? And it's amazing I'm able to read these things with the funny S's. I'm getting better at it. If these add up to less than 2 right angles, then the lines will meet on this side. Conversely, they would meet on this side. If these ones added up to less than 2 right angles. Yeah, had been controversy over the necessity to have this axiom placed in. People thought that this shouldn't have to be an axiom. It ought to be something that would follow from the other axioms, and it should be something that can be proved. And maybe we're missing another axiom or something, but this is something that ought to follow. But the truth of it is that this decision that these straight lines would meet on that particular side is a completely arbitrary one. He could equally have said on the side where they are greater and come up with a different geometry. It would have been maybe strange and unfamiliar. This is the one that is familiar to us. And apparently this can be reworded in the following ways. The 12th axiom can be expressed as well in the following ways. Two diverging straight lines cannot be both parallel to the same straight line. Okay, now I think in modern English, if you would reverse these words, cannot both be parallel, or it could be the translator, the English of the translator who lives in the Falkland Islands speaks, has a different grammar than normal. I don't know. Nowadays, I think that you would say cannot both be parallel. Okay, you understand that? That means we have two diverging straight lines, diverging like this, cannot both be parallel to the same straight line. So suppose this one is parallel to different colored one. Let's say this one is parallel to this one. Then this one cannot be parallel to the green one. Right? They can't both be parallel to the same one, presumably because they're diverging. Again, something that people argued over for ages. And in fact, I don't know for a fact, but I'm nearly certain that these extra ways of saying it were given as arguments as to why the parallel postulate can't be an axiom. Because this obviously is something you can prove, right? Nuh-uh. If a straight line intersect one of the two parallel lines, then it must also intersect the other. Straight line intersects one of two parallel lines. Okay, so that says one of two parallel, right? One of the two parallel must intersect the other. So if we have parallel lines like these, not this, and a straight line intersects intersecting one yet another color, then if I produce this long enough, it should intersect the other one. Okay, that's another way of putting it. Again, an assertion thought before all this business was resolved, to be something that should follow from the other axioms. It should be provable, but there is no way to prove this. And we know that there's no way to prove this because we know that you can drop this you can drop this requirement and the geometry. You can build a geometry that is fully logically consistent and it doesn't have this requirement. The lines, this line might not touch this other one. Only one straight line can be drawn through a given point parallel to a given straight line. Another way of putting it. So one straight line to a given point. So we have a given point P. I can actually put a dot. A given point P, only one straight line can be drawn through the given point, which is parallel to another given straight line. So we have a given straight line. Let's take this one as the given. Okay, get rid of these. Oh, sorry. Doesn't have to pass through. Doesn't have to pass through P. Yeah, through a given and parallel. The axiom says that only one straight line can be drawn through this point and be parallel to another given. Here's the second given straight line. So we're given this and a point, and we are drawing a line parallel to the given line to a given point. Apparently only one line has that. It can be drawn that satisfies that condition. But the truth is that it's possible to develop a system where this condition needn't be satisfied. And that's it for the axioms. We'll accept them as they are. And now go on to see how to use the axioms and postulates to construct the geometry of Euclid. Now, let me just quickly pause this and quickly have a look through this paragraph. Okay, this was one that I wanted to go over, just to reinforce the notion of figure and magnitude, extent, whatever you want to call the measurable quantities. Okay, so now the geometry has for its main objects, the main things, the exposition and explanation of the properties of figure, which is an enclosed finite shape with boundaries. The figure is defined to be the relation which subsists between the boundaries of space. Space, or magnitude, is of three kinds: linear, superficial, meaning a surface, or solid. Right? Now, the bit about angles, I don't know why he says might, but that's what it says. Angles might properly be considered as a fourth species of magnitude. Angular magnitude evidently consists of parts and must therefore be admitted into the species of quantity, which is true enough. It's a type of quantity. However, important bit, the student must not suppose that the magnitude of an angle is affected by the length of the straight lines which include it. Like I was saying before, it is independent of scale and of whole mutual divergence. It is the measure. Oh, okay, so it's just continuing on. The vertex of an angle is the point where the sides or the legs of the angle meet, as in A. Now he just talks about sometimes one letter is sufficient. Sometimes you have to be clear. If I want to express these two together, I have to say E, C, D, with the middle letter being the one where the angle is the vertex. The middle letter is the vertex, like that. Okay, so DCE or ECD indicate this angle. C is unambiguous. I don't need to give G or E or anything. This happens to also be C. Whatever. So that's all explained here, and I think I mentioned this bit about. Yeah, I did. I talked about that. Now I'd like to go and to elucidate some of these ideas and show you that by doing it, the first construction in the book, proposition 1, and I've actually already got them saved, but they're so easy to do. It's easier to just go ahead and do it. Plus, I added a special new feature to my program to speed up doing these sorts of things. All right. Now as you can see that's a great big O. The way to read this, first I'll read it out loud, and then I'll try to interpret it. Proposition 1, Bravo. On a given finite straight line, black, to describe an equilateral triangle. Okay. Now that sounds like backwards English or something, and that's the reason it sounds like that is because there are certain words that are assumed to be there and left out. So I will now read it with the missing words inserted, and all of the other ones contain the same missing words, I think. Problem. On a given finite straight line, the black one, this is how one would describe an equilateral triangle. Okay? So we are going to show by construction how to construct an equilateral triangle just given one line, and the postulates and the axioms and so on. Now, in my program, the best way to make I find to make a flat straight line and not have to have a perfectly steady hand is to draw, let's say 100, 75, 75, because this is double. This will be a flat line, white color, of length, turns out 150. I use white because we're kind of an opposite color, so where he has black, I'll put white. Maybe I can just make the background a bit darker. Choose one of my darker ones. There we go. Nice and dark and clear. So the idea is this. It's quite clever. This one. I'm gonna use my new compass tool. The compass tool works this way. Choose a color. Everything on for my tool has a color. You have to choose a color for every action, and I think that's good because the colors help clarify. First, I select the radial point, the center, and it's a compass. So now I can select another point. Now this is I'm allowed to do according to the axioms. Okay, and now I've described one circle. Next, I'm going to use my compass again with, I don't know, not red. How about blue? I have blue. Green. I'm going to do the same thing with this as the center of the circle. This is a point that I've been given, so I can certainly plot my compass down on it, and I can go to the end of the line and make another circle. That's according to the postulates. Those are abilities that I have. Now, I take my straight edge, which is line, red, let's say, bounded line. I'm allowed to draw from a given point to any other given point. Now, I haven't been given a third point, but we've constructed a third point, which is the intersection of these two circles. So, according to the postulates, I'm allowed to do this. And I'm also allowed to do this. Okay? Now we look at the figure. I should have chose a different color for that one, maybe. But anyway, it's hinting that they're the same. This length here, since it begins at the center of this blue circle and ends at the perimeter of that same circle, this must be one radius distance away from here, and so therefore these two lines are equal, same length. Similarly, for the green circle, which has the same radius as the blue circle, and we follow through the same argument, and these two have the same length, therefore all three sides are the same length, and therefore this is an equilateral triangle. So we have constructed an equilateral triangle. So this here is a demonstration of how to construct an equilateral triangle from a just given one line. Okay? And I'll do maybe three problems. They're quick, as you saw. This one's quite fun. Given any line anywhere in space, okay, so from a given, he doesn't start with the line. He starts with a point. Now you'll notice the way that this is written. This is one way to indicate a point, even though we're not starting with this here. It's identifying the point in the diagram. If we locate the thing that looks like this, the point being referred to will be at the boundary of these two lines. The lines are bounded by points, and the one being referred to is by deduction the only one that stands out of the three in here, the middle one, this. Okay. So all we're given is a line and a point. This is how one would draw a straight line equal to the given finite straight line at the given point. So the ability that we are attempting to add to our toolbox of abilities is if given a straight line of arbitrary length, to reproduce that same line at any given point. Okay? We're going to do that this way. Clear this out. Now I'm going to construct a straight line. Now I'm going to make it a little bit angly. About 13 degrees, length 150. Yeah, okay, that's good. White, I want white. That's his black line. So I can put that here, say, far away, not too far away. And we're given a point, which I could also make white, I suppose. And we make it similar to his diagram here. So we call this, give it a name. Okay, P, and if I wanted to give this a nice fancy L. Now our task is to reproduce this line, not necessarily its direction or anything, but to make a line of equal length starting at P, or ending, such that one of its ends is at P. Okay, and that's the way I understand the problem anyway. Now the way to do that, he uses a dotted line, but I don't have a dotted line facility, but I can use regular lines. We get out our straight edge. Okay, now what I'm going to do is for accuracy, I'm going to just draw straight through it. Given color, I don't know. Doesn't matter what color, because I'm going to delete this one. I want to just draw straight through this, and just to see if I get a good. See, I'm not 100% happy with that, but it's close enough. Now I'm going to draw a bounded line along this one. A different color, red. Not red, close to red. Like that. Delete this one. Go away. Okay, so we're allowed to do that. We can draw a line according to postulate 1 from any given point to another given point. Both of these points were given. Next, what I'm going to do is, I remember because I've done this so many times, is I'm going to construct an equilateral triangle from a given straight line. An ability that I have thanks to problem 1. So I get out my compass and I don't know, choose a color, and I first one with the radial point, radius here and there, and then the other way, different color for clarity. Starting from this side. Then we get out our straight edge. we draw from here to bounded, here, and here to here, and that's an equilateral triangle. So I no longer need these circles. Alright. Now, this thing here, what I'm going to do now is I'm going to draw a circle with this radius. So I get out my compass, and I'll choose this color, and I'm going to start from here and draw a circle this radius. Alright? Now what I wish to do is draw a line from here, extend, which is we're allowed to do postulate 2, I think. We can extend any line for as long as we want, and I would like to extend this red line to the perimeter of this circle. So first I'll do an unbounded thing. Just I find that it's easier to I want a different color, and I want the straight edge. Straight edge. I'll do this. And that looks good, and then I'll put it on bounded, and I'll just follow my own line and delete the extra. Okay. Alright, now I have a line, a yellow line, which is equal to the equal in length to the given line. So we're halfway there. All we got to do is somehow bring this over to here. The way to do that is to get out your compass, trusty compass, and center a circle here at the apex of the equilateral of radius this entire distance. Okay? Now, since this length is the same as this length, I can, if I draw from here to here, these two things will, since they're from the center of a circle, will be of the same radius, and this part of each will be the same. So, I get out my straight edge, and I'll do the unbounded bounded trick. You don't have to, it just helps me anyway, helps me see if I'm doing it right. We don't need you, and we don't need any of this anymore. In fact, get rid of all these things if you can. Okay, now here's our produced line. Now I'm just going to prove that it is of equal size to the given one. And one way to do that is to put them together like this, and get out the compass, and draw a circle with this as the center point. And as you can see, by definition, these two are of the same length. So I did it. I made a line. It was there. You saw, and this is just a double check. But the end result was I had that line not that line, this line, brand new line, at P having the same length of a given line. So we take an arbitrary line at any point, and we now have the ability to create another one of the same length at any point. Right? One more, because it uses that last result, and it's pretty quick. Here, we are given two lines from the greater of, it's not totally clear the way it's written, but the way what it's saying is from the greater of this, which is a black line and a blue line, to cut off a part equal to the less. So we have a big line and a little line, a greater and a lesser, and we want to develop a procedure to cut off from the greater of the two a part equal to the less. Okay, so chopping, we want a chopping block. To do that, I'm supposing use this. Oops, not this one. This is good for drawing flat lines. Let's suppose let's suppose this is the grader. Okay, here's the grader. No, it's not big enough. How about yeah, this would be 200 long. Okay, here's the grader, and the less. Let's say I'll do it. Oops, wrong direction. I'll make the lesser one not that color though. Like this, similar to the problem. What we want to do is cut off from this one the trailing bit. Find a procedure to do that. Okay. Now, in the problem, I don't know if it's intentional, but the lesser one was at 90 degrees, like this. Okay, and this one we're given. Okay, we're given these two lines, right? A greater and a less, and they're not in the same place or anything. However, by the previous problem, I can reproduce this line at this point. Okay, doesn't matter how, but I mean it doesn't matter how it's going to end up there. There is a way for me to get this over to here. It might not be perpendicular, it might be at an angle, but that doesn't matter, because what we do is we get out our compass, and I don't know, but even if it was off it might be off in a direction like this, but we get the compass out and we put this, select this end as the center of a circle and of radius the lesser. Okay, and now we have constructed this point from which we can now produce this line. It'll be in this color if you want. I can now draw a line bounded from here to here, and it's underneath there. Here. Okay, that was that was our task, and that's essentially what I had there. If we imagine white is black, there would be dots here, and just slightly beside this, I produced a line which is the lesser of these two lines, long. Or another way of saying it is that I've cut off the extra bit. So we added now that ability to our toolbox, and that's exactly the proof as explained here. We draw here, which is equal to this by problem 2. See? Using problem 2, draw this. They don't give an angle, it doesn't matter. All it is important is that we can now describe the circle using our compass, and that circle identifies where we need to cut off from our line the extra amount to make our line the same length as this line. And so we did it. And that's some Euclidean geometry. It all works like this. We're developing abilities and tools, and as we go along, as you can imagine, the tools and the abilities get more and more complex and more intricate, and our power to do things becomes really quite strong. Things you thought impossible suddenly become a piece of cake. Right now can't do very much, but there's 6 books worth of problems here, and I'm sure by the end we should be able to do some pretty cool stuff and prove some pretty interesting theorems about geometry. Okay, that's for this one. See you next time.